Okay, class, we are starting the second half of chapter 2 of journal 3. Okay, so we're going to start to be able to understand another interpretation or understanding of our derivatives. We have partial derivatives, and those put together make a gradient. And now we're going to have a way of visually and geometrically understanding those. And before we get to that, though, we need to cover the topic of tangency in R3. So again, back when life was a little bit simpler, we were in R2, y was a function of x. In the xy plane, here's a function. We could stop at any point and draw a tangent line. And those were real important for us. They helped us find extrema, they helped us find critical points. They were essential in concavity, where it's increasing and decreasing, all sorts of descriptions of a graph. And now we're going to talk about in R3 tangency. So what is that going to mean? So let's think again, we're back to z as a function of x and y in 3 space. So let's think of a couple surfaces. So this orange, imagine this is a perfect sphere. So what's the equation of a sphere? Hopefully remember this from chapter 1, x squared plus y squared plus z squared. So it starts like the circle, adds the third component, makes the third dimension. Let's say it's 9, so it'd be a circle centered at the origin with a radius of 9. If we solve for z to write its explicit function, z is a function of x and y, we'd have the square root of 9 minus x squared minus y squared is the top half, or the top hemisphere. And we could take the negative, is the bottom hemisphere. And so you can cut your orange in half and think about that way. Or we could, I'm going to use a upended cereal bowl and imagine that this is actually not plateaued there, it's a perfect hemisphere. So if it's the top half, that'd be the z equals positive square root, and this would be the bottom, the lower hemisphere. Okay, so we are going to, just like you did here, you stop at a point, in this case x, on the function. We're going to stop at a point, in this case x and y, on the function, which is a surface this time. So if I stop at any point on this surface, and we talk about tangency, can you see my point there? Some point on the surface, we want to know, how do we define tangency then? So back in the R2 case, we had a tangent line, but how many tangent lines go through that point? Well, there's one, there's one, there's one. And there are infinitely many tangent lines that would sweep out a tangent plane. And then we want to think about what types of tangent planes are we really interested in R3. Well, so let's think about this. If I ask you how many vertical tangent planes are there on this, so here would be one, here's one, here's one, here's one, all the way around the ring that would be like the diameter of this surface, all the way around this ring, when it's in its upright position, everything there would be a vertical tangent plane all the way around. It's actually a surface or plane. How many horizontal tangent planes are there on this surface? There's one at the top and one at the bottom. We're going to be interested particularly in those horizontal tangent planes. Those are ones that are more interested than the vertical ones. We're going to figure out how we're going to find these horizontal tangent planes. They're going to be keys for us. So let's take a surface. Let's do our familiar surface. Find the tangent plane. Because again, we can't just ask about lines back here. We're now in higher dimensional space. We'll ask about tangent planes. And over in R4 or R5, we'd say tangent hyperplanes. But we're in R3 for this familiar surface. We've looked at several times in the journals and several times in our video lectures. Circular paraboloid facing down up at 6. At a particular point though, right? I can't just say find the tangent plane. I have to give you a point that I'm interested in. So let's say at the point 1, 2, be the xy. And I'm actually in 3-dimensional space, so I should go ahead and get the z that corresponds to this, right? for every xy, there's one and only one z that does that here. So I'm really figuring out what f of 1, 2 is. So I plug in 1 for x, 2 for y, and I get 6 minus 1 minus 4 is 1. So on this surface, which I'm just drawing a section, again, we know it continues on infinitely down like that. This is z-axis, x, y. We're at 1, 2, 1. So somewhere on the side of that circular parabola, we're at this point. And we want to get the actual equation of the tangent plane. And so we know what it looks like. We can visualize it here, but we want to actually compute the linear function that describes it. And so there's going to be a rule here, and this is in your journals. There's a box that if you want to get the equation of a tangent plane at the point A, B for some surface, you're going to get your partials and evaluate it at the point on the surface. So this is in general at any A, B, but we're at the point 1, 2 for x and y. You evaluate your partial, do x minus a, evaluate your partial y, do x minus y minus b. So we'll put a little space over here for our partials. F sub x at any xy was minus 2x, so f sub x at the point of tangency right here at 1, 2 would be minus 2. F sub y at any xy is minus 2y, and f sub y at the point of tangency 1, 2 would be minus 4. And then it's just a matter of using this, this boxed formula. We already figured out f of 1, 2 was 1, and we plugged in here, so we have 1. Z is going to be 1 plus f sub x at 1, 2, we got minus 2. X minus 1, that's our a value, plus f sub y at the point 1, 2, which was minus 4. Y minus the point of tangency, the y value of the point of tangency was 2. And so we can solve this. Let's simplify a little bit, and then let's check graphically that this makes sense. Minus 2x plus 2 minus 4y plus 8. So z is minus 2x minus 4y, 3, 11 plus 11. All right, so let's see what that looks like. So you can graph this. You did really good on the last module 1 activities, plotting these planes, no problem. You can find intercepts and plot it. But let's actually plot it on the surface with a tech tool. So I'm going to share my screen, and we will go to Calc Plot 3D. All right, so let's get rid of that one. Let's do a new function. Z is a function of x and y. Let's put our original circular paraboloid facing down. And let's zoom out. Let's get rid of hide all objects so we don't see any of that anymore. Turn that guy on. So there's our circular paraboloid up the z-axis at 6 facing down. And then let's go ahead and put our plane on. So let's add another function. Z is a function of x and y. And what did we get? Negative 2x plus, or sorry, minus 4y plus 11. Put that one in, and let's zoom out a bit so we can see. Maybe let's change the color of this guy. Yeah, it's a little better. And using Lane's trick here, we can see it a little better. And see that it does just touch. And let's go ahead and put on a point just to be sure. So let's select, add the point. The point of tangency was 1, 2, 1. So 1, 2, 1. Yeah, and right there. Okay, so we see that the math worked out as it should visually, checks for us. And you can also do this automatically with Calc-Plot 3D up here. Let me see. Show the tangent plane at a point. Okay. So you can, back to your XY 2D description here, you pick points, and you can watch that it shows just a little section of the plane moving around as you move around the surface. It's going around the back of it, so it's coming back around the front. There you go. And notice as I move that up here on the top, it's showing the equation of the plane, which is always linear because it's a plane, linear in the X, the Y, and the Z. And then it's also showing the point that you're at. So when, let's see, let's do, when X is 2, Y is about -2, it gives the Z value, is minus below the XY plane here at -1.7 something. And then it's showing you the expression of the tangent plane as well there. Okay, stop. Okay. One last thing here we'll do Calc-Plot 3D is to talk about non-differentiable points. What happens when you're at a point on the surface that is non-differentiable? So go back to Calc-Plot 3D. So this was a surface, again, our familiar surface, no problem. Derivative can be captured everywhere, but let's look at something like an absolute value. So let's turn all these guys off. Add a new one. Let's say like 2 minus absolute value, which hopefully you already have an idea in your head, kind of what that would look like. Pause the video for a moment and think about it. You should be able to figure that out with like translations and shifts and so forth. So let's come back here. Look at that. Here's the tangent plane on the surface. The tangent plane is the surface, no problem. Let's see. Come up here. All objects first, and then come back and put the tangent plane back on so we can see the tangent equation. So it is just the equation of the plane at that point. The plane is x plus z equals 2. That's the positive part. Now, again, as I move this point, let's see what happens up here along this ridge, which is kind of funny the way it's even displaying it with these teeth. It's kind of having a hard time showing that's a ridge line of a roof. And right up there at the ridge line, here in the figure in Calc-Plot 3D, that is actually a non-differentiable point. You can't really take a derivative there because the tangent plane is different. As you approach from this side of the roof, the tangent plane, look, oops, my tangent plane. As you approach that, the tangent plane's looking like this side of the roof over here, the green side. But if you jump over here, the tangent plane is looking like the other side. So the tangent plane changes, it flips, and it's an abrupt change. Anywhere that there's that it's a cusp or a corner, abrupt change, it's not a smooth surface, then we have a non-differential point. So everywhere along that ridge line, there are actually infinitely many non-differentiable points for this absolute value function, and it's right along that ridge line. And so, again, the tangent plane's shown up at the top, and I just want to show what happens when we get close to that ridge line, and then you flip over. Because they're so, the tangent plane changes approaching from the left to the right, we don't actually have one exactly at that point along the ridge line. So if we were to enter 0, and then for y, 0, it won't, it does it, it sort of breaks Calc-Plot 3D. If you try to ask it to give me something at a non-differentiable point, yeah, it says no tangent plane equation exists there, and it won't even show the graph. It kind of goes a little haywire. So again, just to show you that most of the surfaces we're going to be looking at evaluating, taking derivatives of, will be smooth, but there are some of these examples that you might encounter in real life that have sections where they're non-differentiable. Okay, that's the end of this mini lesson.